In the previous video in this series on principles of description and inference, we looked at how to calculate the power for the test of a proportion. In this video, I want to speak more generally about the role of power in research studies. Let's start with the definition. The power of a hypothesis test is the probability that the test correctly rejects a specific null hypothesis when a specific alternative hypothesis is true. In the previous video, we used the null hypothesis that the population proportion is equal to 0.50. We used the specific alternative that the proportion in fact is indeed 0.65 rather than 0.50. And to test the null hypothesis, we used a nominal type 1 error rate, that is the maximum probability of a type 1 error, of 0.05 or 5%. We found that if we have 15 observations, the power is only 17%. That is, if the actual true proportion in the population is 0.65 and we take a random sample of 15 participants and observe them and categorize them as success or failure, the probability that we'll be able to reject the null hypothesis that the success rate is 0.50 or 50% is only 17%. As you can see from this example, power is about rejecting a null hypothesis that should be rejected. The null hypothesis is typically about no effect or a trivial effect, and so rejecting it says that we've actually determined there is a treatment effect. If we're only able to reject the null hypothesis 17% of the time, when there is in fact not only a treatment effect but a fairly large one, that's not a good state of affairs. This means there's a high probability that we'll be making a statistical error, because we should be rejecting the null hypothesis, but the chance of doing so is quite small. Let's look at the types of errors that we can possibly make. A type 1 error is rejection of a null hypothesis that is true. Since the null hypothesis is typically that there is no treatment effect, or at least that the treatment effect is too small to be considered important, then when we reject that null hypothesis, we determine there is an effect. You can see how this is considered the most serious type of error that we can make, saying that there is a treatment effect when there's not. A type 2 error may not be considered as serious as a type 1 error, but it is still an error that we want to avoid. It is retention of a null hypothesis that is false. If a null hypothesis is false, and the null hypothesis is that there is no treatment effect, if there is a treatment effect, we should in fact detect it by rejecting that null hypothesis. A type 2 error means we did not reject the null hypothesis, and we should have, therefore we did not detect the treatment that exists. When we retain a null hypothesis, we don't state that we have proven the null hypothesis, so you can see that this is not as serious of an error because we're simply going to retain a null hypothesis that we should have rejected. We're not saying it's true. On the other hand, a type 2 error is something we want to avoid because if we keep making type 2 errors, we do not make progress with our science. We do not detect things that we should be detecting. It is like looking through a microscope that doesn't have enough power to see what is under the microscope, and so you say there may be something there, but I don't really know for sure. You need more power. The same is true in research studies. If we're not detecting effects that are there, we need more power. We can control the probability of a type 1 error by setting the nominal type 1 error rate, that is, the maximum probability of making a type 1 error, and we symbolize that with alpha. Most commonly, alpha is set to 0.05 in the behavioral, social, and medical sciences. It's seen as the industry standard. We can also control the probability of a type 2 error, and we do that through a variety of design factors and anticipation of the effect size, as I will talk about in just a moment. First, let's look at the symbol for a type 2 error. That is beta. A beta value of about 0.20 or less is considered acceptable in most research in the behavioral, social, and medical sciences. Now, this relates to power directly. Power is 1 minus beta. If the acceptable standard for beta is 0.20, then the acceptable standard for power is for it to be at least 0.80 or 80%. We want the probability of detecting a treatment that is actually there to be at least 80%, just like we want the probability of detecting a treatment that's not there to be no more than 5%. I mentioned that the type 2 error, and thus power, is controlled through a variety of design factors and anticipation of the effect size. Here are the many things that can influence power. The size of the treatment effect. The bigger the treatment effect, the more the power. The number of observations that we're able to randomly select from the population. The bigger the number, the more the power. The chosen level of confidence, or the maximum type 1 error rate. If we allow for a higher type 1 error rate, not necessarily a good thing, our power will go up. We have to strike a balance. Now, all of these other power influencers that I've listed here have to do with the variation of the response measure that we're using. Consistency of the treatment implementation. If it is inconsistent, we will have more variation of our response measure. If our measurement is not reliable, we will have high variation of our response measurement. Higher variation of observational characteristics, such as the time and place when we record the measurement, could influence the variation of the measurement, as could extraneous variables that are included in the study. If you include more extraneous variables in the study, you can account for the variation in the response measure that is due to those variables, thus decreasing the amount of variation in the response measure of interest. The heterogeneity of participants. The more homogeneous your population, the less variation we expect to see in the response measure. The more heterogeneous the population, the more variation we expect to see in the response measure. And then the individual characteristics beyond control and measurement, such as the attitude of participants and their willingness to be cooperative in the study. Here I am showing you two normal distributions. These are meant to represent the possible distribution of a response measure. And you notice that one of these normal distributions has higher variation than the other. That is, one or more of these power influencers are such that you have more variation in that distribution than you do in the other distribution. The rule is this: the less variation in our response measure, the more power. Therefore, this distribution that has less variation will have more power. Now note that these items that can influence power can be controlled through non-statistical means. They can be controlled by the design of your study, by the way you implement the treatment, by the measures you use and the measurement process, by the way that you standardize conditions when you measure participants. All of these are non-statistical in nature, but they all influence power. Usually when people think about what influences power, they think about how to increase the power in a statistical calculation. And when you do that, you focus on three things: the effect size, the type 1 error rate, and the sample size. If you set any three of those, we can do a statistical calculation to calculate the power. Similarly, if you set any three of the four, power, effect size, type 1 error rate, and sample size, you can calculate the fourth one. We're going to focus here on calculating power from these other three. But let's also not forget that behind the scenes in the study, there are all these other power influencers that the researcher has some level of control over them. And so we shouldn't just go immediately to our statistical calculation of power without first thinking about those other influences. When we think about the relationship of effect size, type 1 error rate, and sample size to power in a statistical calculation, we are assuming we have established the variability of our effect size estimate and it will not change during the study. So we are assuming that we have now done everything we can about those power influencers in order to increase the power of the study, and now that's constant. Then we can turn our attention to these big three. Let's look at each of them in more detail. Increasing an effect size requires changing the intervention that is at the heart of the study. Yes, you can get a bigger power calculation by just predicting a larger effect size, but if you're predicting a larger effect size without actually doing anything to increase the effect size, that's disingenuous. Predicting a larger effect just to increase power can be research dishonesty and can be unethical. Increasing the type 1 error rate is not unethical because we are going to announce to the public what we used as the type 1 error rate, but it's typically frowned on by practitioners in the discipline who want it to be set at 0.05, though I would argue that it may be justified to increase the type 1 error rate to 0.10 or even 0.20 when the sample size is necessarily small because of a small population or limited access. Yet the primary focus we will take when we want to increase power is on the sample size. Increasing the sample size, that is the number of observations that you can make, is the preferred method for increasing the power of a study. Now, a larger sample size frequently translates into higher costs, so sample sizes are often limited by the research budget. What I typically tell my dissertation students who ask me to help them do a power calculation is, what is the maximum number of observations you can afford? That is, how big of a sample size can you afford? And if they tell me the maximum sample size that they can afford, and then we look realistically at the size of the effect that either they think they're going to get or the minimum effect that they think is still important to their study, and then if they set the type 1 error rate at a value of, say, 0.05, and we do the calculation and the power is low, they probably should not proceed with that study and should look elsewhere. I have had situations where the power comes out to be 0.50, and I tell the student, just ask your committee if you can stand in front of them and flip a coin to determine whether or not you reject the null hypothesis, because that's basically what kind of power you have in this study. So focusing on the best way to increase power, that is by increasing the sample size, let's look at a power curve that shows power increasing as a function of sample size. Here I am using the same null hypothesis and the same alternative hypothesis that I did in the last video. The null is 0.50, the alternative is 0.65, and the type 1 error rate is 0.05. Remember, in that video, we only had 15 participants, thus we ended up with a power of 17%. And you can see that here on this graph. You can also see the discrete nature of our data as the power jumps up and down in discrete steps. But as we get larger and larger sample sizes, the power becomes more and more like a continuous function. If I want to keep my type 2 error at no more than 0.20, then I want my power to be at least 80%. So here I have drawn a line at 0.80 for 80% power, and I want to find the sample size at which the power will no longer drop below 0.80. And as long as I have at least that many observations in my sample, I'm good. We can get a rough approximation of what that is on this graph. It appears to be something around a sample size of 75 participants, but we can get a more precise number by following the power calculation that I showed in the last video and making sure we're indeed at 80%. There are two types of power calculations that are typically used in research studies. One is what I call a priori power. That is, power is calculated when designing the study. In the best case scenario, it's used to determine the sample size we need in order to obtain adequate power so that we can make sure we get that many observations when conducting the study. A priori means before the fact, before the study. But another type of power calculation that is often done is post hoc power. That is, after the study has been conducted, we use the calculated estimates to determine what power the researcher had going into the study. I do not have a favorable view of post hoc power at all. I would consider it the first in my list of power shenanigans. Calculating post hoc power. For one thing, you're not calculating a probability because you've already observed the data. The study is over. So calculating post hoc power in order to determine that you had enough power going into the study, well, you're not actually calculating power because that is a probability statement. Instead, what you're doing is you're saying, if I had done this power calculation before I started the study, and if I had used as my estimates all the values that I eventually found in the study, then this would have been the power. That's not very helpful at all. Furthermore, if we end up determining that we had low power, which tells us You don't have a very good chance of rejecting the null hypothesis. What's that statement mean? You're already done. You either rejected it or you did not. If you find you had high power, does that mean kudos to you? You had high power? No, you either rejected the null hypothesis or you did not. I have heard of situations where even reviewers of manuscripts ask for post hoc power calculations, and I think it's rubbish. It's one of my power shenanigans. Another one is increasing the estimate of the effect size for the purpose of increasing our estimate of power. We don't do anything to the treatment in order to increase the effect, but yet we don't have high enough power, so we're going to mess around with the effect size until we do. I already mentioned that I consider this unethical practice. There are other things we could adjust in ways that are not necessarily realistic, such as the relationship of covariates to the response. The higher the relationship, the more we expect the covariate to account for variation, and thus, the more it will influence and increase our power. But if we're just adjusting those in order to increase power, if we're thinking, hey, I don't have enough power, I bet that relationship is really higher than I said at first. Then again, you're wandering towards that unethical and dishonest line. Something you can do is use larger number of variables. We know that as we increase the number of variables in a study, we are increasing the amount of variation in the response variable that is accounted for. But what if those variables have no theoretical importance? Then they have no place in our study. There's all sorts of examples of nonsense relationships among variables. And in my view, if you include such variables in a study, you're starting to merge into that nonsense region. Researchers can increase the validity of positive research outcomes by establishing a worst-case scenario rather than a best-case scenario. I recommend that when you do power calculations, you consider worst-case scenario, not best-case scenario. And that way, when you end up with a better situation than you had anticipated or that you had stated in your power calculation, your power will go up, not down, and ultimately your research will become more defensible.